Assalamu alaikum students. In today's lecture, first of all we will do one of the numerical related to the Planck's quantum theory as given in your book as an example, and then the topic of X-rays will be discussed under the headings of discovery, the relation with atomic number, Moseley's law, and then the origin of the X-rays, and then uses of X-rays. Now here the example is given. A photon of light with energy 10 to the minus 19 joules is emitted by a source of light. A part is convert this light into wavelength, frequency and wave number of the photon in terms of meters, hertz and per meter respectively. So for this the data is mentioned over there as a solution. It is given. Here it is. Energy of photon is given, that is represented by E. It is 10 to the minus 19 joules. You have to find out lambda, that is wavelength, frequency, that is the nu, and nu bar, that is the wave number. Now the units are also being mentioned here. Similarly, the B part says convert this energy of photon into hertz and calculate the wavelength in centimeter, frequency in hertz, and wave number in per centimeter. So you have to change the equation and the units in it, right? So first of all, we will give the solution for the first one, A part. Now here you can see the frequency in hertz or the wavelength is given. Frequency in hertz you have to calculate by the use of this equation, that is E is equal to h nu. We have only given the value of energy, that is 10 to the minus 19 joules, right? In it rearrange this equation to find it out frequency by arranging it as frequency is equal to E by h, where h is the Planck's constant having value 6.626 into 10 to the minus 34 joules second. After solving this, you will get the answer 1.51 into 10 to the power 14 per seconds only is left, as the joule will also be cancelled out, right? Now here, or you can also call it as hertz, right? Now here, wavelength calculations is done by means of this equation, that is nu is equal to c upon lambda, right? So take out lambda outside so that the equation will turn like this. Lambda is equal to c upon mu. C is the velocity of light and mu is the frequency of radiation, which we got from the previous one. Previous one equation, that is E is equal to h nu. The frequency of radiation is 1.51 times per 14 per second, while the velocity of light is 3 into 10 to the 8 meter per second, right? After doing this calculation, you will get the answer only in meters, as the s minus 1 will be cancelled, right? So the answer is 1.98 into 10 to the minus 6 meters. Now you have to remember this value of lambda to be used for the wave number calculation. Here it is given. Wave number you can find by this formula, nu bar is equal to 1 upon lambda. So it will be, as it is given in meters, so now as it is in the denominator, so it will come as per meter, right? Now here we have to just change the units in case of the solution for B part. Energy will be converted into hertz, wavelength lambda will be converted into centimeter instead of meters, frequency will stay in hertz. First it was in per second or hertz, now it will be again in will be hertz, and wave number you have to calculate in the form of per centimeter instead of per meter, right? For this, what you have to do, first of all, you should know the relationship. 1 joule is equal to 10 raised to the power 7 ergs, right? 1 joule is equal to 10 to the power 7 ergs. So what will be the amount of energy? E is equal to E 10 raised to the minus 19 multiplied by 10 to the power 7. You will get there. After this multiplication, the exponents will resolve like 10 to the minus 12 erg will be the answer. Similarly, Planck's constant was given under the heading of joules per second. Now you have to convert it into erg second. So what you have to do? You have to multiply it once again with 10 to the power 7 erg to convert joules into erg. Right? Now here the answer is given in erg second, that is H is equal to 6.626 10 to the power minus 27. Frequency, you have to find it out once again as you have changed the terms of the units. So again use the same formula, add the values and you will get your answer in the form of per second once again for the frequency. Now to calculate wavelength in centimeters, convert the speed of light from meter into centimeter. 1 meter is equal to 100 centimeter. So the value is given as 3 into 10 to the power 10 centimeter per second. And the value of frequency will be taken from the previous one equation. So you will get value of lambda in centimeters. It is 1.98 in 10 to the minus 4 centimeters. And for wave number, as the value of the lambda is in centimeter, so here you have to give the equation nu bar is equal to 1 upon lambda. So 1 over 1.98 into 10 to the minus 4 centimeters. So the value will be 5 into 10 to the power 3 per centimeters. Right? I hope you are familiar with the definitions of frequency, wavelength and wave number. Frequency is the number of waves passing through a point per second, while wavelength is the distance between two crests or two troughs, while wave number, it is the reciprocal of the wavelength, right, or the number of unit passing through a unit distance, that is termed as the wave number. The next topic is of X-rays. X-rays were discovered by Wilhelm Röntgen, who was a German physicist. In 1895, accidentally, the X-rays were discovered. For this discovery, he was awarded Nobel Prize in 1901. He was working on a Coolidge tube, or it is also called a vacuum tube, in which the construction of this tube is given as it is, that it consists of a cathode which is having a tungsten metal placed in front of it. A heavy anode is placed in front of it, which is having the metal which is having high atomic number, that is placed in front of it. Now it is adjusted in such a way, or it is arranged in such a way, that the rays which will come out of this cathode, they will hit the target by means of the 45 degrees angle. So all the rays will concentrate on one point, and then it is attached with a battery, this one, to produce a high voltage. As the process is the exothermic one, so it will become heat up. To avoid the collapse of the system, here it is provided with the water pipes or the water tubing behind. Now what happens here, that these rays are being produced when cathode rays which are coming out of cathode, they are supplied high electricity and they pass through that of the tungsten metal. They are accelerated. When they hit the target, they are going to produce the uh, rays which are of unknown nature, and they are directed in all directions. So these rays at that time, due to their unknown nature, were termed as X-rays. Right? Now here, next one is how these X-rays are produced. What is the theory about it? Now here it is given. It says that when an electron, which is highly energetic electron, which is coming out of the cathode ray, that hits the metal atom. Look at this metal atom presented here. It is having two orbits in which the electrons are residing. When these cathode rays, which are coming out of cathode, they hit this electron and this atom of the heavy metal anode, what they do, they strike to the orbitals, and they kick out one of the electron of the inner shell of this system, so making it unstable. Now you can see the two arrangements are here. In the first one arrangement, the first one, you can see here the after the removal of the electron from this metal atom, the configuration has become destabilized, or it has become unstable, as one of its inner electrons gone. So to fulfill this empty place, one of the electron from the higher energy level moves down there to the lower energy level, and in doing so, one of the photon of energy is released to come out in the form of the X-rays. So this is how X-rays are generated, right? Now here, now these are the properties of X-rays are given. The X-rays are the electromagnetic radiations. Electromagnetic means having no charge upon them, of very high frequency, and energy means they are very energetic rays, right? Secondly, the energy and the wavelength of X-rays depends upon the nature of anode. Heavy is the anode particle, the stronger will be the radiations coming out of it, and high will be the energy of the radiation, and shorter will be the wavelength. You know very well what the relationship of frequency and wavelength is. Shorter is the wavelength, higher is the frequency. Longer is the wavelength, shorter is the frequency, right? Now the third one is every metal has its own characteristic X-rays. Yes, because some of the metal will have the lower atomic number, they will have the X-rays with the less energy, while the other one which are having the heavy metal particles in it, they will give the high energy X-rays, right? Then X-rays are emitted from the target in all directions, only a part of it used by means of the windows, right? Now the next one is here, the relationship between that of atomic number and X-rays, that was found by Moseley, right? He did a comprehensive study of the X-rays in 1913, and it covered the range of the wavelengths 0.04 to 0.08 angstrom, right? Moseley determined the atomic numbers of the elements using these X-rays, which were produced in cathode rays tube when the electron beam falls on a metal target, right? He found the spectral lines. Now, यहाँ से जो radiations which are coming out in the form of X-rays, they were actually passed through that of the prism to give us spectrum, that will be a continuous spectrum which is produced by them. He found the spectra of the 38 different metal elements, that is from aluminium to gold, Au, right, as the target. Means these metals were placed as a node which were hit by the cathode rays, right? So different spectral lines were produced. As you can see in this graph, there is given that the frequency of the X-rays is directly proportional to the number of protons in the nuclei. Here it is given atomic number as it is on increase, and here the frequency of X-rays. So they have a direct relationship with each other. As the atomic number is on increase, the frequency of radiation is also increasing. The frequency of radiation is also increasing, means more stronger are the rays produced, right? So he found that it depends upon the atomic number, that the more is the number of proton in the center, greater is the frequency of the radiations, right? Now here some of the conclusions of Moseley's analysis is given. As you know that the different one orbits are present in the atom. The nearest to the nucleus lies K shell. Then next onward is L shell, M shell, and N shell. Then onward, the other shells are also there. If we say the shorter wavelengths are being produced, shorter wavelength means highly energetic rays are produced, means the electron from the inner orbit is kicked out, and to replace it, the electrons are coming out from the outermost shells to the K shell. So the series is termed as the K series. You can call it as K alpha or K beta as the two lines are being given out. That near to the next to the K shell is going to give electron to this K shell, or next higher electron is being coming to this K shell. Similarly, lines of the longer wavelengths can also be generated over there when L orbital is observed, that it is releasing its inner electron, and then electrons from the higher one orbits, they are coming to this L shell, right? So then it depends upon that greater is the frequency of the radiation or the lower is the frequency of the radiation. The distance between the orbits will determine the energy of the photons generated. If the target metal is of higher atomic number, the frequency of radiation will be higher, right? Moseley formulated a relationship between frequency and atomic number of the elements. This is termed as the Moseley's law. According to this law, the square root of frequency of a spectral line or a spectra, that is in X-ray spectrum, that varies as the atomic number of an element emitting it, right? So here it is given under root with mu proportional to that of z. Z is the atomic number. You can also say it as under root mu is equal to a in the bracket z minus b. A and b, they are the constant quantity. Now, the Moseley used the X-ray spectroscopic technique to find out the atomic number of the elements. This X-ray spectroscopy technique was discovered by Max von Leu, so that he got the help from this technique to find out the atomic number of the elements, right? Now come to the practical applications of X-rays. Here it is given. After the discovery, the other scientists, they started to find out the practical applications of X-rays. As you know very well, they are the highly penetrating rays, so they can be used to photograph interior of an object, as it is used as X-rays in the surgical assistance, right? Since X-rays, they have different penetrating power, so they can be used to photograph interior of an object, as I told you earlier. So here we have one of the X-ray of a broken arm, so they can help to the surgeries for the broken parts of the body. Now, X-rays also helped in determination of the crystal structures. Crystals are formed of the closely packed particles in particular layers in a three-dimensional space having specific areas or the specific points, right? Now, according to the Max van Leeuw, it was thought that in the particles in the planes in the crystal, they might be separated by a distance that is of the magnitude as the wavelength of the X-rays, right? Means the different planes are there which can be separated by means of the wavelength of the X-rays, which will be helpful to break these planes, right? Or so that a beam of X-rays should be diffracted by a crystal, right Ji? Now this was quickly verified experimentally, and a diffraction pattern of crystal was obtained on a photographic film, how the X-rays are diffracted from that of the uh, crystal structure, right? And from proving that the particles and the planes of crystals, they are symmetrically arranged. The pattern is termed as the Leu pattern of the particle. Here the term is given. This is an X-ray source. Here this one is the crystal which is placed over there. That is a nightfall prism, you can say, which is placed. Here it is a photographic plate. The diffracted beams, they are coming out and they are falling upon it. On this photographic plate, they are producing a pattern of the arrangement of the different planes and that of the particles in the crystal structure, they are determined. The two persons, that is William Bragg and Lawrence Frank, in 1913 in England, they devised a simple apparatus to find out the internal structure of a crystal, and the technique was named as X-ray diffraction technique, as it was being discovered by man Max Van Leeuw, and then it was applied by the William Bragg and Lawrence Bragg to determine the crystal structure, and the term was given as X-ray diffraction technique, in which X-rays, when they fall upon a crystal, they produce a photographic evidence, that is the diffracted one rays, they are coming out to show the pattern of the crystal, and in which how the planes as well as the particles, they are arranged in three-dimensional space in the crystal. That is being called X-ray diffraction technique. Once again, it depends upon that the planes and that of the particles of the crystal, they have the equivalency with that of the wavelength of the radiations, that is of X-rays. So when they fall upon them, they can be diffracted easily, right? So this is what we call as X-ray diffraction technique. This is all about the X-rays. Learn it well and then ask me if you have any questions.